In this lesson, we're looking at slope fields from first order differential equations. So basically, we're going to focus on being able to construct a slope field using an array of coordinates and a differential equation. And then we'll look at showing how we determine a particular solution on a slope field. And we'll do that by considering a family of solutions. Now, I'll start by just breaking down the scenario. So for any differential, dy dx is equal to f of x, g of y, so a separable differential equation. When we look at the general solution, then that general solution represents a family of solutions. So if we look at a really simple example here, let's say we're looking at dy dx is equal to y. And the solution to that is, as we all know, we've done this enough times now, 1 on y integral dy, and we end up with 1 dx. So that's ln y and x plus c, and we end up then with y equals ae to the power of x as just a quick solution. Now, the reality is that a here is a parameter, and that parameter is determined by knowing a value of x and y to be able to create the specific solution or the particular solution. So what this does is it represents that family of solutions, and what we're basically saying is where a is an element of a set of real numbers. Now, it can't always be every value, but that a or the c value from that integral process can then be represented by a set of unknown values, and that set of unknown values can be shown as a field. So that can be shown as a number of possible solutions. So in this case, if we look at a is equal to 1, it goes through at 1. A is equal to 2, a is equal to 3, a is equal to 4, a is equal to 5, and we get a bunch of different solutions. And if we flip that around, we end up with more solutions. So when a is negative 1, a is negative 2, a is negative 3. And even though this is a pretty messy representation, we can look at all these different solutions. Now, when we look at a field diagram, we're using rates of change to represent the same thing. And we can draw that field diagram by looking at what that curve will be doing at all these specific points. But there's probably a better way to do it. And the better way is to look at it as an array of slopes. So looking at this same space, going between, let's say if we looked at it between negative 2 and 2, and that would be 2, 1, 0, negative 1, 2. And we looked at the rates of change for each of these. So in this case, we'd be looking at dy dx is equal to y. So it's pretty straightforward. It's whatever the y values are. So here we've got x and y. So all these would be the same. They'd all be 2s. These would all be 1s. These would all be 1s. These would all be 0s. These would be negative 1s. And these would be negative 2s. So when we go to sketch this slope field, it's pretty straightforward. What we're looking at here is gradients of 2, gradients of 1, gradients of 0, gradients of negative 1, and gradients of negative 2. Now, this might be a little bit difficult to see, but if we then look at a specific solution, so if we look at a solution when x is equal to 0, y is equal to 2, and we put that in for that specific solution, we end up with 2 is equal to ae to the power of 0, so a is 2, and we're looking at y is equal to 2e to the power of x. So that means it can be represented by a line passing through these rates to be one specific solution within this slope field. All right, so hopefully that makes sense. What we're doing is we're looking at the slopes at particular points. So when we move on and we look at example 1, it's another rather simple one. We're looking at to sketch the slope field for the differential equation dy dx is equal to x on 2. And we're looking at between negative 2 and 2 and negative 2 and 2 again. We'll first look at this general solution. So the general solution, in this case, we're looking at 1 dy, and we're looking at the integral of x on 2 dx. So this becomes y, and we've got x squared on 4 plus c. So we end up with y is equal to 1/4 x squared plus c. So it should look like a parabola. Now if we set up our grid again, we've got x and we've got y. We've got -2, -1, 0, 1, and 2. And 2, 1, 0, -1, and -2. When we sub this in and it's just x on 2 for each of them, we've got -1, -0.5, we've got 0, 0.5, and 1. And that would be the same for all of them. So -1 all the way down, doesn't matter what the y values are. -0.5 all the way down, zeros all the way down, 0.5 all the way down, and 1s all the way down. So when we go to draw this, these are all -1s. So -1s are about on that 45-degree angle. We've got -0.5s, which is half. We've got zeros, we've got halves, and then we've got 1s. So if we look closely there, we can see these parabolas. And say, for example, I'm looking for a particular solution or a specific solution where x is equal to 0 and y is equal to 0. Then we end up putting this in, and we end up with 0 is obviously 0 plus c, so c is equal to 0. And we're looking at y is equal to 1/4x squared. So if we go to graph that 1/4x squared, when x is equal to -2, we end up with 1/4 of 4, which is 1. When we put in -1, we end up with 1/4. When we put in 0, we get 0. We get 1/4 again, and we get 1. And so there's a specific solution that goes through the middle of that field. Now, if we broke this down, so we weren't just using integer values, and we started using smaller values here, we'd end up with those slope values on those exact points. But that slope field is just meant to give us an idea of the shape of the function. Okay, so we'll look at one more example. In this case, we're going to, it says use a calculator, but we can do it without it because we're smarter than a calculator. And we're looking at 2y dx is equal to -x on 2y. And it wants us to show this specific solution, but we want to sketch the field first. We'll draw it again between -2 and 2. So -2, -1, 0, 1, and 2. And 2, 1, 0, -1, and -2. So when we sub in x is -2 and y is 2, we end up with 2 on 4, so we get 0.5. We've got 1 on 4, 0.25. We've got 0, -0.25, and -0.5. When y is 1, we've got 1, 0.5, 0, -0.5, and 1. When it's 0, now we can't divide by 0, so we end up with a line of not possible. When it's -1, then we end up with -1, -0.5, 0, 0.5, and 1. And when we put in -2, we end up with -0.5, -0.25, 0, 0.25, and 0.5. So now if we go to sketch this fella, and we start at -2, 2, so -2 and 2, we're saying that it's a positive slope of, and we'll just put in these values, so bear with me. It usually makes it easier to put the points or the coordinates where you have to draw the slopes. So here we've got 0.5, 0.25, 0, -0.25, -0.5. And then we've got 1, and 0.5, and 0, negative, and -1. We've got nothing on this line. Now, when you think about it, that's not possible. Basically, when we're talking about slope, it's straight up and down. Now, the only one we're not going to worry about is that 0 divided by 0. We definitely don't want to talk about that today. And when we flip that around, we've got -1, -0.5, 0, 0.5, and 1, and -0.5, 0.25, 0, 0.25, 0.5. So I'm hoping you can see that this starts to look like an ellipse. If we went through and we got our general solution, we would find that we ended up with a basic ellipse function. Sorry, a basic ellipse relation. All right, so now if we look at the solution x equals 0, y equals 1, we can go through and do this. So let's look at our general solution. We've got 2y dy, and we've got negative x dx. So we've got 2y squared on 2 is equal to negative x squared on 2 plus c. And so we end up with y squared plus x squared on 2 is equal to c. And when we divide by c, we end up with y squared on c plus x squared on 2c is equal to 1. And so that's where our ellipse function comes from. And the c value is looking at the major and minor radii in this case, so the a and b values. Right, so when we let x equals 0 and y equal 1, we've got 1 on c plus 0 is equal to 1. And we end up then with 1 on c is equal to 1 and c is equal to 1. So that means when we put that back in, we end up with y squared on 1 plus x squared on 2 is equal to 1, which means that the a value is square root of 2 and the b value is equal to 1. So we end up with an ellipse that looks something like, but not exactly like, this. And you can see that slope field gives an indication of that shape. All right, so hopefully that makes sense. That's basically what we're doing with slope fields. So we need to be able to draw on those specific solutions. We should be able to draw a basic slope field given that differential equation. And again, the best way to do it is with that array. So set up that table and work out what those gradients are. We can draw them quite quickly. Thank you.